GCE Advanced Level Chemistry Practical Series, experiment number 22. Experimental observation of different oxidation states of manganese containing compounds using redox reactions. The aim of this experiment is to observe the different colors of manganese compounds in different oxidation states and how to interconvert between these oxidation states. Now, let's take a look at the next slide. Over here, we have some information about the electronic configuration of manganese. Manganese is the 25th element. Atomic number of manganese is 25. So therefore, the electronic configuration, as you can see, is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 and 4s2. As you can see, there are 2 electrons in the 4th quantum shell, and before filling the 4th quantum shell, we have 5 electrons in the 3d subshell. When you take a look at the different oxidation states of manganese, we can see how the electrons are being removed. Since we have 2 electrons in the outermost quantum shell of manganese, the very first oxidation state that we observe is +2. As these 2 outermost electrons can get removed, you will produce a manganese +2 oxidation state after removing the outermost electrons or electrons present in the 4th quantum shell. And afterwards, you can proceed to remove 1 electron at a time from the 3d subshell. So as you can see, when 1 electron from the 3d subshell is removed, we come across our +3 oxidation state. When 2 electrons are being removed, we come across our +4 oxidation state, so on and so forth. Finally, students, we come across the +7 oxidation state, somewhat of a common oxidation state for manganese. And this oxidation state, we have the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, which is a noble gas electronic configuration, or in other words, which is the same electronic configuration of argon. So therefore, this happens to be somewhat of a common oxidation state of manganese. And over here in this table, you can see the uncommon oxidation states of manganese included in parentheses. So students, while keeping that in mind, we can move on to our experiment. Now, experiment number 22, if you are trying to conduct it in your school laboratory, you will be needing this equipment. You will be needing test tubes and a glass rod. Instead of a test tube, you can also use a boiling tube. Glass rod is needed to stir the solutions that you take into your test tubes or the boiling tubes. And we have these following chemicals for this experiment. We need dilute potassium permanganate solution, KMnO4. We'll be using dilute sulfuric acid, H2SO4 solution, concentrated sodium hydroxide solution, or sodium hydroxide pellets. Right, we can use either one of those. We can use concentrated, highly concentrated actually, sodium hydroxide, or in other words, we can use sodium hydroxide pellets. As we conduct this experiment, since we need a higher concentration of OH- ions, we can proceed with either highly concentrated sodium hydroxide solution, or we can directly add sodium hydroxide pellets into the test tubes that require highly concentrated OH- ion medium. And we have hydrogen peroxide solution as well as concentrated HCl acid solution. Now, let's see what the first step of this experiment is. Take about 2 cubic centimeters of dilute potassium permanganate. So we are going to be taking 2 cubic centimeters of dilute potassium permanganate to a boiling tube, and the color of the solution is purple. Very important to notice the color, right? We have the color written over here. potassium permanganate, when you take it to your test tube, you would notice the color very clearly. It is a purple color solution. And the reason for the color is given here, which is the permanganate ions. Potassium permanganate has its characteristic purple color due to the presence of permanganate ions, MnO4 1-. So these permanganate ions are at the oxidation state +7, or manganese's oxidation state in permanganate ions is +7. So therefore, at this particular oxidation state, manganese happens to be purple in color, or in other words, permanganate ions happens to be purple in color. So after making this observation, we can move on to the next step. In the next step, students, we are going to take our dilute potassium permanganate solution and add a little bit of dilute sulfuric acid. So we are going to add dilute sulfuric acid to this aqueous potassium permanganate medium. So after acidifying potassium permanganate, we are going to add highly concentrated potassium hydroxide or sodium hydroxide. We can add either one. We can add sodium hydroxide, concentrated sodium hydroxide, or we can add concentrated potassium hydroxide. Either way, the main purpose is to make the solution extremely alkaline. Like I mentioned earlier when we were talking about the chemicals or the reagents we'll be using, we can use potassium permanganate or sodium hydroxide, and at the same time, instead of using potassium permanganate or sodium hydroxide solutions, we can use sodium hydroxide pellets, because as these pellets dissolve in the potassium permanganate medium, they will produce a highly alkaline medium. So you have the option of going with either one of those options. Let's say we take concentrated potassium hydroxide and we add concentrated potassium hydroxide until we observe a color change. So we can see when potassium permanganate is reacted with concentrated potassium hydroxide, there's a redox reaction that is taking place, which converts permanganate anions into manganate anions. So the reaction would be potassium permanganate converts into potassium manganate, K2MnO4, and potassium hydroxide contains hydroxide ions. These hydroxide ions convert into oxygen. So students, keep in mind that this is a redox reaction that is taking place. Potassium permanganate contains permanganate anion, which is purple in color, and potassium manganate contains manganate anion, which is green in color. And as you can see over here, potassium permanganate contains manganese in +7 oxidation state. As you can very clearly see here, potassium permanganate contains manganese in +7 oxidation state. And when it comes to potassium manganate or manganate anion, it contains manganese in +6 oxidation state. So +7 to +6 is a reduction. And when this reduction is happening, an electron is being taken in. And when we take a look at hydroxide ions, we see hydroxide ions converting from OH- to oxygen. So in OH-, the oxidation state of oxygen is -2. And if you take an oxygen molecule, the oxidation state of oxygen in the oxygen molecule is 0. So you can see when hydroxide ions converted into oxygen, it has gone up in oxidation state, meaning this is an oxidation, And potassium permanganate, when turning into potassium manganate, it has gone down in the oxidation number, meaning it is a reduction. Now let's learn how to balance this kind of redox reactions. Now students, if you take a look at this, you will notice the first chemical reaction you observe, or first part of the redox reaction that you would have observed, is potassium permanganate turns into potassium manganate. So over here we show the oxidation state as +7. Oxidation state of manganese was +7, and now it is at +6 oxidation state. There's a reduction that is taking place, and we can say this involves uptake of 1 electron. And at the same time, we have, when it comes to observing the reduction reaction, we should know, when it comes to talking about redox reactions, we have to understand when the redox reaction is taking up electrons, there has to be an oxidation reaction that is releasing electrons. So over here, OH minus ions or hydroxide ions are the ones who are undergoing oxidation. So a hydroxide ion actually converts into an oxygen molecule. As there are 2 oxygens over there, we can take 2 hydroxide ions on this side as well. The oxidation state of oxygen atom in the hydroxide ion is -2. We observed this earlier. And the oxidation state of oxygen or oxygen atoms in the oxygen molecule is 0. So students, now you will see when one oxygen atom turns into an oxygen atom in the oxygen molecule, the oxidation state goes from -2 to 0, -2 to 0, which means it releases 2 electrons. However, to make one oxygen molecule, you would need 2 oxygen atoms, meaning 2 hydroxide ions ends up releasing 4 electrons. 2 electrons each multiplied by 2, it ends up releasing 4 electrons when producing one oxygen molecule. So there is the involvement of 4 electrons. So students, you can see the oxidation reaction releases 4 electrons, but the reduction reaction is taking only 1 electron. This does not necessarily agree with our redox reaction rules. So therefore, we'll have to make sure the number of electrons that are given out by the oxidation reaction as well as number of electrons that are taken in by the redox reaction is the same. Meaning, we will have to multiply this specific reduction reaction by 4 so that the number of electrons that are taken in matches the number of electrons that are released. So when I try to multiply this equation, I will have to put a 4 in front of potassium permanganate, and I'll have to take 4 manganate ions as well, so I have to include a 4 in front of potassium manganate. Now let's try to balance this. So when you're trying to balance this equation, you are going to notice that on the right hand side, the number of manganese atoms are 4, and on the left hand side you have the same number. And if you bring our attention to potassium, the number of atoms of potassium on the right hand side is 8, but the number of atoms of potassium on the left hand side is 4, meaning we have to add 4 more potassium atoms onto the left hand side. Now students, potassium came into the medium in 2 ways. we added potassium permanganate, which is one way in which potassium actually can come into the medium. And the other way in which potassium was added to the medium was through the addition of potassium hydroxide. So since we can't change the number over here, because if you change the number of potassiums over here, it will affect the number of potassiums over here again, as well as the number of permanganate or manganate anions over here as well. So therefore, we would not change the number that we have over here. Instead, we turn to the other source of potassium in this medium, which is potassium hydroxide. So we have hydroxide ions here. So hydroxide ions actually come into the medium through potassium. So we can straight away write 4 potassium hydroxide. We have 4 potassium hydroxide coming into the medium, and now the number of potassiums are balanced. So after balancing the potassiums, we can turn to oxygens. So you have altogether 4 into 4, we have 16 oxygens here, and there's 2 oxygen atoms over here. Altogether, the number of oxygens is 18. Now, let's take a look at the number of oxygens on the left-hand side of the equation. 4 into 4, we have 16 oxygens here, and we have 4 oxygens here, which means overall number of oxygens on the left-hand side is 20. This tells us the number of oxygens on either side is not balanced. So to balance that, we can add water to the right-hand side. So we have enough and more water in the medium. At the same time, we have to add 2 water molecules, as there's a deficit of 2 oxygen atoms on the right-hand side. Now, the number of oxygen atoms on either side would be balanced. However, the number of hydrogen atoms are yet to be balanced. Let's see if the number of hydrogen atoms on either side is the same. Now, on the left-hand side, we have 4 hydrogen atoms, and that's it. On the right-hand side, we have 4 hydrogen atoms coming from the water molecules. So either side, the amount of hydrogen atoms are the same. This would tell us the equation is now finally balanced. Now, this is how you can balance a redox equation using oxidation numbers and observing the number of electrons that are being exchanged in each of the oxidation and reduction reactions. Now, let's move on to another way in which we can actually solve this equation or balance this equation. Now, that is through observation of the oxidation reaction and reduction reaction separately, and we are going to write half equations for both of the reactions, and then we are going to learn how to balance a half equation that is happening in alkaline medium. Now, first of all, let's write our reduction reaction. So the reduction reaction was, we have potassium permanganate turning into potassium manganate. Now students, since we are going to be only, now when it comes to a method like this, after understanding that this is mainly focusing on reduction and oxidation reactions only, we will have a main focus on the ions. So you do not necessarily, at the beginning of this equation, you don't have to include all of the ions together, meaning the positively charged potassium ions does not have to be included here, because the main focus here is the oxidation number change that is happening, or the reduction reaction that is happening between permanganate ions between our permanganate ions and manganate ions. Over here, when you see permanganate turns into manganate, you can see all of the atoms on either side is balanced except for the charges. So when it comes to balancing a half equation, one thing that you need to keep in mind, unlike normal other chemical reactions, we have to pay close attention to balancing the charges. We only have over here potassium, or we have permanganate ion and we have manganate ion there. They basically have the same formula except for the charges, meaning the charges have to be balanced across the equation. So we have one negative charge over here, two negative charges over there. So therefore, if you are to balance the number of negative charges on either side of the arrow, you have to add an electron to the left hand side. So there's one negative charge over here, there's another negative charge coming through the electron. Altogether, you have two minus negative charges, or two negative charges on the left hand side, and over here you have two minus charge on the right hand side as well. So therefore the charges, negative charges, are balanced. This is your reduction reaction. We can call this reaction number 1, reduction reaction. And then we can move on to our oxidation reaction. Now in oxidation reaction, we have OH minus ions turning into oxygen molecules. Over here, students, you might have noticed the oxygens are not balanced. So we can start with that. We have one OH minus ion on the left hand side, contains only one oxygen atom. Right hand side has two oxygen atoms. So to balance this, we can put a 2 in front of OH minus. And when you do this, you can notice the oxygens are balanced. Now the hydrogens are not balanced. So if you have learned how to balance these kind of half equations in acidic and alkaline medium, you would know you have to add H pluses to balance the number of hydrogens on either side. So over here we have to add 2 H pluses to the right hand side. But is it correct to add H pluses in an extremely alkaline medium? The answer would be no. As this is an alkaline medium, H pluses won't exist freely available like this. They will react with OH minuses, and we are going to be adding 1 OH minus per H plus. So we are going to be adding 2 OH minuses, 1 for each H plus. So if you are adding OH minuses to the right hand side of the equation, it has to be done to the left hand side of the equation as well. So if you're doing something to the right hand side, the same has to be done to the left hand side. So we added 1 OH minus per H plus that we added over here, which means we have to add 2 OH minuses onto your left hand side as well. Now students, these two H plus and OH minus ions together will form water molecules. So there will be 2 water molecules formed when 2 H pluses are combined with 2 OH minuses. So now we can rewrite this equation. We can rewrite this equation in the following manner. We have 2 OH minuses over here and 2 OH minuses over here. Altogether we have 4 OH minuses, or 4 hydroxide ions, 1 oxygen molecule, and 2 water molecules. Alright, so we can erase this now. We can see, if you now pay attention to the atoms on either side, we have 4 oxygen atoms over here, we have 2 over here, and another 2 oxygen atoms over there. altogether the number of oxygen atoms are balanced. 4 on this side and 4 on the other side. If you take a look at the hydrogen atoms, on the left hand side of the equation there are 4 hydrogen atoms. On the right hand side of the equation, each water molecule brings 2 hydrogen atoms. So there are 2 water molecules bringing 4 hydrogen atoms. Hydrogen atoms on either side are also balanced. The only thing that is not balanced here is the charge. On the left hand side we have 4 negative charges. On the left hand side we have overall 4 negative charges. On the right hand side we have 0 charges. So charges are obviously not balanced. So to balance the charges, we can add electrons to the side where there's less negative charges. On the right hand side we have 0 charges, so therefore we can add 4 electrons to bring in 4 negative charges. Now we can see on either side the charges are balanced, and therefore this equation or half equation is now balanced. So we have written 2 half equations by now, students. One is our oxidation reaction. We can call it the reaction number 2, right? So the reaction number 2 is releasing 4 electrons. This is an oxidation reaction. And if you take a look at our reaction number 1, which we have over here, it is our reduction reaction, which is taking only 1 electron. This reaction is releasing 4 electrons. This is taking only 1 electron. So since the number of electrons are not balancing here, we have to multiply the first equation by 4, so that the number of electrons that are taken in happens to be 4. So let me write that equation over here after multiplying the first equation by 4. So I'm going to write that we take the first equation and you multiply it by 4, which brings us this equation, right? Let me write it a bit more clearly more towards the left hand side. We can take the first reaction, multiply it by 4, which will produce this equation, which is 4 electrons plus potassium. Oh, we do not necessarily include the potassium, plus permanganate, an ion, turning into manganate, an ion. Since we multiplied it by 4, both have to be written multiplied by 4. Now we can see we have taken this first equation, multiplied by 4, produced this third equation. Now students, all that is left to do is adding these two. We can now add these two reactions together. When you're adding these two reactions, you would notice that certain chemical species are getting cancelled off, or certain parts of each of these equations are going to get cancelled off. Now let's take a look at what happens when we're adding these two equations. You can see over here there are 4 electrons on the right hand side of an equation, and on the second equation there are 4 electrons on the left hand side. So when they are present like that on opposite sides of the two equations, they can get cancelled off. And over here we can see there are no other parts that are present on opposite sides of the arrow, meaning there's nothing more left to cancel off. So you have over here 4 hydroxide ions plus 4 permanganate ions, and we have 4 manganate ions with 1 oxygen and 2 water molecules. Now students, still this is in ionic format. This is the balanced ionic equation. If you want to convert this into a balanced chemical equation, we can do so by adding the necessary ions. Now, hydroxide ions came into the medium with potassium hydroxide. So, whenever you see hydroxide ions, you have to accompany hydroxide ions with potassium. So, now you have potassium hydroxide. We have 4 of them here. And then permanganate ions were accompanied by potassium as we added potassium permanganate. Our initial solution that we took was potassium permanganate. So therefore, when you have 4 permanganate ions, that means we have taken 4 potassium permanganate. Again, at that point, we have manganate anions, and manganate anions will join with the positively charged cation in the medium. So what do we have as the positively charged cation in the medium? We have potassium ions. So we can write K2MnO4. As we have 2 negative charges with each permanganate ion, we are going to join 2 potassiums. So that is why we have K2, and then this 4 belongs to permanganate ion. So we have 4 manganate ions. So therefore, when you take 4 manganate ions and join with the relevant number of potassiums, we are producing K2MnO4. Actually, we are producing 4 potassium manganate over here. And then the oxygen number remains the same. There's nothing done to oxygen or water. So now we can observe that we have gotten to the same chemical, balanced chemical equation that we obtained through the oxidation number method. This is the second way of coming to the balanced chemical equation. Normally, moving forward, we are going to be using the oxidation number method for balancing the equations, as this method includes a few additional steps. However, you should be aware of how to balance a half equation in alkaline medium and in acidic medium. So what we have looked at over here is how to balance a half equation in alkaline medium. Now, let's move on to the next step. In this step, students, we are going to learn what happens when we take our potassium manganate solution and react it with hydrogen peroxide. Before we move on to this step, students, there is something that is very important for me to share with you. That is, we know potassium permanganate is something that you commonly find in the labs. You actually are very familiar with potassium permanganate because we use it all the time as an oxidizing agent. And we saw in the previous reaction also, the potassium permanganate got reduced while potassium permanganate was acting as an oxidizing agent. So since we use potassium permanganate quite a lot, I'm pretty sure all of you are very familiar with potassium permanganate. However, you might have not necessarily come across a lot of potassium manganate. This is because potassium manganate is stable in extremely alkaline medium. This is why even in the previous reactions we saw potassium manganate was produced in highly alkaline medium, or when we reacted potassium permanganate with concentrated alkaline medium. This tells us potassium manganate, the green color solution that we have here. Now potassium permanganate is green color thanks to this manganate anion, and this manganate anion is stable in highly alkaline medium. If you try to dilute that alkaline medium, or if you try to acidify this alkaline medium, it will again undergo a few chemical reactions that will change potassium manganate to potassium permanganate and manganese dioxide. We'll be looking at this reaction as well towards the latter parts of this chemical, towards the latter parts of this experiment. So keep in mind, students, potassium manganate is stable in highly alkaline medium. That is something to make note of. Now again, we are here. So we have taken our potassium manganate solution. Over here, we produce this potassium manganate solution in highly alkaline medium. Still, in this test tube also, we have potassium manganate in that same highly alkaline medium. And we are going to be adding hydrogen peroxide to this potassium manganate solution. Now, let's take a look at what happens when we react this alkaline potassium manganate solution with hydrogen peroxide. As I was mentioning earlier, we have potassium manganate. So in water, you can see this dissociates. We have potassium manganate, potassium manganate can get ionized or dissociate into two potassium ions and manganate ions. And these manganate ions are the ones that are responsible for the green color of this solution. Now that is one thing to keep in mind, and the same thing happens when it comes to potassium permanganate. Potassium permanganate also dissociates in water to form potassium plus ions and permanganate anions, and permanganate anions happens to be purple in color. We looked at that earlier in the beginning of this experiment. Now students, after keeping this in mind, we can see here the chemical reaction that is taking place. We have potassium manganate reacting with hydrogen peroxide and turning into manganese dioxide, potassium hydroxide and oxygen. So manganese dioxide is what manganate ions are turning into. Manganate ions are turning into manganese dioxide. And manganese dioxide is actually brown in color, as well as it is going to be a solid. Manganese dioxide is a solid and is brown in color. So in this chemical reaction, what you're going to be observing is the green color of the initial reaction disappears while forming a brown color precipitate and a colorless solution. However, students, when you are actually doing this in the lab, the MnO2 or the manganese dioxide solid particles that are produced while this reaction is happening is extremely small. They are very fine particles of manganese dioxide. So these fine particles gets suspended in the aqueous medium evenly, making it look like a brown color or light brown color solution has gotten formed. However, keep in mind, when you see this as a brown color solution, it is not necessarily a brown color solution. It is this manganese dioxide fine solid particles being suspended in the aqueous medium, giving us an illusion that we have actually produced a brown color solution. However, if you wait for a while to all of the manganese dioxide solid particles to get collected at the bottom, then you would see a colorless solution with a brown color precipitate. So again, to keep in mind, when you're doing this experiment, you might observe the formation of a brown color solution, but keep in mind it is not a solution. It is in fact the solid particles that are brown, which is MnO2 solid particles, are suspended in aqueous medium, making it look like it is a brown color solution. If you let it sit for a while, all of the solid particles will collect at the bottom, and you will see that a brown color precipitate was in fact formed along with a colorless aqueous medium. We have potassium hydroxide and oxygen formed as well. So you will see gas bubbles being formed. That is the evolution of gas that we see here in this reaction is due to the production of oxygen. Now students, let's take a look at the chemical reaction that is taking place. The reaction that is taking place over here is also a redox reaction. as mentioned earlier when we were starting this reaction or this experiment. This experiment, we interconvert the oxidation states of manganese with the help of reduction reactions, with the help of redox reactions. And what you see over here is also a redox reaction. We can see potassium manganate, or more specifically, the manganate anion contains manganese in the +6 oxidation state. Now, it converts into manganate anion converts into manganese dioxide, and over there manganese is at +4 oxidation state. So it has gone from +6 to +4, +6 to +4, which is a reduction in the oxidation number. So therefore this is a reduction reaction, and we can say potassium manganate is acting as an oxidizing agent while it is getting reduced. Hydrogen peroxide has oxygen in 1- oxidation state. Keep in mind, students, you normally see oxygen when it comes to water and all other types of oxides in the oxidation state of -2. However, when it comes to peroxides, it's something that you should note down. When it comes to peroxide, oxygen is at -1 oxidation state. So peroxides, oxygen, when it comes to oxygen present in peroxides, have -1 oxidation state, and it converts into a 0 oxidation state when peroxides get converts into oxygen molecules. So since it is going from -1 to 0, it is an increase in the oxidation number, which means this is an oxidation that is taking place. So this is an oxidation. The previous reaction that we were looking at, where potassium manganate formed manganese dioxide, that reaction is considered to be a reduction. So when potassium manganate is reducing, it is acting as an oxidizing agent. When hydrogen peroxide is getting oxidized, it is acting as a reducing agent. Now let's learn how to balance this equation. Students, we have hydrogen peroxide turning into oxygen. So in this case, you can see it goes from -1 to 0. So this is reduction, involves 1 electron each. So we'll get to that in a second. I have to make one more point clear before we get to the number of electrons. Just take a look at the oxidation state for the time being. And we have potassium manganate turning into manganese dioxide. So over here the oxidation state is +4, and when it comes to potassium manganate, oxidation state is +6, and this is our reduction. So when the reduction reaction is happening, you can see there's an involvement of 2 electrons as the oxidation number comes down by 2. So since oxidation number goes from +6 to +4, there's a reduction of 2 oxidation numbers, meaning there's an involvement of 2 electrons. 2 electrons are being taken in this reduction. And in the oxidation, each oxygen atom goes from -1 to 0. This happens to each oxygen atom. And in forming of 1 oxygen molecule, you need to take 2 oxygen atoms. So since each oxygen atom is releasing 1 electron, when an oxygen molecule is formed, there's the release of 2 electrons. Now, we can very clearly see when the oxidation reaction is happening, they release 2 electrons, and those 2 electrons can be taken in by the reduction reaction. So the number of electrons in the oxidation and the reduction reaction balances, which means there's no more balancing to be done in the part of electrons. Now we have to try and balance the atoms that we have over here. We have one manganese on the left hand side as well. We have 2 potassiums, and we do not have any potassiums on the right hand side. So we can add potassium since there's no other ions present here. But since this is an alkaline medium, you have enough and more hydroxide ions. So we can couple the potassium ions with hydroxides and produce potassium hydroxide here. And now we can take a look at the other reagents. But before that, we have only included 1 potassium hydroxide, but the number of potassium here is 2. So we have to be careful and include the number 2 in front of potassium hydroxide, so the potassiums are properly balanced. So now we can go ahead and see if hydrogens and oxygens in this equation is properly balanced. Let's move towards hydrogen. So you can see there are 2 hydrogens on the left hand side of the equation, and there are 2 hydrogens coming in from potassium hydroxide. So hydrogens are balanced. On the right hand side, we have 4 oxygens over here and another 2 oxygens over here. So altogether we have 6 oxygens. And on the right hand side, we have 2 oxygens over here. There are another 2 over here. And since we take 2 potassium hydroxide, there will be another 2 oxygens coming in from potassium hydroxide. Altogether, the number of oxygens on the right hand side is also 6. So you can see on both sides, the oxygen number is also balanced. So since we don't have any charged species over here, we do not have to balance the charges. We only have to balance the atoms when it comes to this particular equation. So this is how you can balance an equation like this using the oxidation numbers. Now students, with that, we move on to this slide, where we will talk about the different colors that we observe at different oxidation states of manganese. Now, we initially took a potassium permanganate solution into a boiling tube or a test tube, and we observed the color to be purple. And this was due to the presence of permanganate ions. Permanganate ions contained manganese in +7 oxidation state. So we can say when it comes to the manganese's +7 oxidation state, the color that you observe is purple. We have a purple color observed when it comes to potassium permanganate. It contains a permanganate anion, which will bring in the color purple. Just to repeat, potassium permanganate contains permanganate anion. Permanganate anion contains manganese in +7 oxidation state, and the color of permanganate anion is going to be purple. So we have written the oxidation state of manganese here. And second time around, when we were carrying out the experiment, we added concentrated potassium hydroxide, and in this highly concentrated alkaline medium, potassium permanganate converted into potassium manganate. And potassium manganate contained manganate anions. Manganate anion contained manganese in +6 oxidation state, and the color that was observed was green. So the manganate anion, MnO4 2- anion, is going to be having a green color. And later on, we took a small sample of potassium manganate solution, alkaline solution, might I add. It is reacted with hydrogen peroxide. And when hydrogen peroxide is added to potassium manganate solution, potassium manganate or manganate ions converted into manganese dioxide. Manganese dioxide has an oxidation state of +4, and manganese dioxide is a solid. So manganese dioxide contains manganese in +4, and the color that we observe when it comes to manganese dioxide is a brown color, and it is going to be a solid, so we can observe it as a brown color precipitate. Now later on in the next chemical reaction that we'll be doing in the next part, we'll be converting manganese dioxide into Mn2+ ions. Manganese dioxide gets converted into manganese 2+ ions. Now manganese 2+ ions, when present in aqueous medium, comes into contact with water ligands and forms a complex ion. And that complex ion's formula is given over here. Manganese is coupled with 6 water molecules, or forms coordinate bonds with 6 water molecules, and forms hexa aqua manganese 2 ion. This is a complex ion. So this complex ion has a color which is pale pink. The color intensity of this complex ion is extremely low. So although we say hexa aqua manganese 2 ion has a pale pink color, most of the time when we are conducting these experiments where we produce manganese 2+ ions in the aqueous medium, we would not end up observing this color. However, if you take extremely concentrated Mn2+ aqueous ion solution, you might observe a very slight pale pink color in the aqueous medium, but that is at extremely high concentrations of Mn2+ ions. When you are normally conducting these kind of experiments in the lab, if you produce Mn2+ ions, the solution that you observe, the final solution being colorless whenever you are producing Mn2+ ions, that is due to the color intensity of Mn2+ ion solutions being very, very low. It appears colorless. While keeping that in mind, we are going to be moving on to the next reaction, which is going to be adding concentrated hydrochloric acid to a suspension that contains MnO2 precipitate. So even in your textbook, it mentions that we will be adding hydrochloric acid to not a solution of MnO2, because MnO2 is going to be a solid. However, this solid is suspended in the aqueous medium, so we'll say we're adding it to a suspension that contains MnO2 precipitate. Because in the lab, when we are doing these experiments, you will notice we'll be producing a suspension where you have the MnO2 precipitate suspended evenly across the aqueous medium, making it look like a brown color aqueous solution. However, it is not a solution. Now, observing, when you are conducting this experiment, you will be observing the following observations. The brown color precipitate disappears. As MnO2 reacts with HCl, MnO2 converts into Mn2+ ions. So therefore, the brown color precipitate will disappear. Brown color precipitate was there due to the presence of MnO2, manganese dioxide. However, if you react it with HCl, since all of the manganese dioxide will react with HCl, the brown color precipitate will disappear. And we can see the evolution of a colorless gas. Right? The colorless gas that is evolved is going to be chlorine. So a few gas bubbles will be observed when you are conducting this reaction. And a brown color MnO2 precipitate reacts with HCl to form Mn2+ ions. And we do know Mn2+ ions are supposed to be pale pink in color. However, due to the low concentration of Mn2+ ions produced over here, you will not observe that pale pink color. Instead, you will be observing a colorless solution being formed. But when it comes to writing answers at your exam, keep in mind you have to write the color of Mn2 plus. Mn2 plus aqueous ion solution, or the complex ion of Mn2 plus, which is hexa-aqua manganese 2 ions, are pale pink in color. You cannot write it as colorless. You have to write the hexa-aqua manganese 2 ions are going to be pale pink in color. Right, so over here, students, you observe the chemical reaction that is taking place. You will have a brown color precipitate in the initial reactant we are taking, which is MnO2. And when you add concentrated hydrochloric acid, we can see the brown color precipitate MnO2 dissolves to form manganese chloride, right, which is MnCl2. So MnCl2 in water actually is present in the following manner: MnCl2, which is an aqueous solution, which means in the aqueous medium, Mn is present as Mn2 plus ions in the medium, as well as Cl minus ions. 2 Cl minus ions will be present in the medium, along with 1 Mn2 plus aqueous ion. So these manganese ions are the ones that will end up forming a complex ion with water ligands, hexa-aqua manganese 2 complex ion. So this hexa-aqua manganese 2 complex ion is supposed to be pale pink in color. In the lab, when you're doing the experiment, it appears colorless. So these are the observations you should be aware of when conducting this experiment. Now, let's move on to balance this equation. How to balance this equation. Since this is done in acidic medium, I will teach you how to balance an equation like this in acidic medium. We have MnO2 turning into Mn2 plus. And over here, there are 2 oxygen atoms on the left hand side, but there aren't any oxygen atoms on the right hand side. So therefore, we can add those oxygen atoms by adding water molecules onto the right hand side. So when you add water molecules onto the right hand side, students, the number of oxygens are balanced. However, we are now introducing hydrogen atoms into the equation. So to balance the hydrogen atoms in the equation, we can add H plus ions over here onto the left hand side. Since there are 4 hydrogen atoms, I have to add 4 H plus ions onto the right hand side of this equation. Onto the left hand side of this equation. So on our left hand side of this equation, we have 4 H plus ions. So therefore, overall charge on the left hand side is going to be plus 4, and overall charge on the right hand side is plus 2. Why is it plus 2? Because manganese 2 plus ion brings in 2 positive charges. Over here, all of the positive charges are brought in by H plus ions. And since this is an acidic medium, we can add H plus ions into this side without any issue. So students, after balancing number of atoms, since we do not have the charges balanced, we have to proceed to balancing the charges. On the left hand side, we have 4 plus charges. On the right hand side, we have 2 plus charges. So we have to bring both of the charges to the same value. In order to do that, we can add 2 electrons onto the left hand side of the equation. When you do that, we have 2 negative charges coming in from the 2 electrons, and altogether the overall charge of the left hand side of the equation will end up being 2 plus. So now on either side of the arrow, the charges are also balanced. You have plus 2 charge over there as well as a +2 charge on the left hand side of the equation. Now we have written down the half equation for our reduction reaction. So now students, after writing down the reduction reaction, we can move on to the oxidation reaction. What was the oxidation reaction here? We saw the Cl minuses in HCl getting converted into chlorine, Cl2. So this is our oxidation reaction. And since there are two chlorines on the right hand side, the left hand side should also contain two chlorines, and the overall charge over here then becomes -2, and over here there's no charge, 0 charge. And to balance that off, we can add 2 electrons over here. Now we have 2 minus charges on the right hand side as well. So now the charges are balanced, and therefore the oxidation half equation is also balanced. Now we can observe that the reduction reaction and oxidation reaction have similar amounts of electrons, meaning the amount of electron that is released by the oxidation reaction and the amount of electrons taken in by the reduction reaction are the same. So when we are adding these two reactions, we can actually cancel off these electrons that are present either side of the arrow, and then we can move on to addition of these two reactions, half equations. So you can see there are 4 H pluses. We have 4 H pluses on the left hand side, and then there's 2 Cl minuses. We have 1 MnO2. On the right hand side, we have 1 Mn2 plus, 1 Cl2, and 2 water molecules. Now this is the balanced ionic equation, and if you want to write the final balanced equation, we can do so by coupling each of these ions with their complementary ion. So you have H pluses. Now H pluses came into the medium when we added HCl. So when you write 4 H pluses, and we have 2 Cl minuses as well over here, but if we add 2 more Cl minuses, we are going to get 4 HCl. We are going to get 4 HCl. And we have 1 manganese dioxide. Now manganese that we have over here is present in the medium as Mn2 plus, and it can couple with the negatively charged ions in the medium. In a highly concentrated acidic medium, which was acidified by adding HCl, what is the most commonly available negatively charged ion? Cl minus ions. So therefore, we can couple the manganese 2 plus ions with 2 Cl minus ions or chloride ions and form manganese chloride. And then you have 1 chlorine molecule along with 2 water molecules. Now we have written your final balanced chemical equation. Now let's see if it is actually balanced. We have 4 hydrogen atoms. We have 4 hydrogen atoms on the right hand side as well. We have 4 Cls, and we have 2 chlorine atoms over here along with another 2 chlorine atoms over here. Altogether 4 chlorine atoms are balanced. 1 manganese, 1 manganese, 2 oxygens on the left hand side and the 2 oxygens on the right hand side coming from water. So this is your final balanced chemical equation. Now I followed the half equation method to get to the final equation. As we learned how to balance a half equation in the alkaline medium earlier, I wanted to show you how a half equation can be balanced in the acidic medium. When it comes to the acidic medium, you should add H pluses to balance the hydrogens. Now students, let's move on to this equation again. We have the same equation that we discussed a little while ago. Over here, we have very clearly indicated how the oxidation number of each species change. We have Mn in manganese dioxide having an oxidation number of +4, changing to an oxidation number of +2 when it converts into Mn2+. And we have HCl, and we have chlorine in HCl with oxidation number of -1, changing into an oxidation number of 0 when it turns into chlorine molecules. So HCl turning into chlorine gas is our oxidation reaction, and manganese dioxide turning into Mn2+ or manganese chloride is our reduction reaction. While manganese dioxide is turning into manganese chloride, it is acting as an oxidizing agent, and when it comes to HCl turning into chlorine gas, it is acting as a reducing agent. While keeping it in mind, we can now move on to our next reaction. In this slide, students, we have a summary of what we have learned so far in this experiment. We have taken permanganate anions, which were purple in color, and we have converted into manganate anions. How did we do this? We did this by adding concentrated potassium hydroxide. So we did this conversion in alkaline medium. In the initial reaction, when we were doing this, we added small amount of acid into the potassium permanganate aqueous medium. We added this acid, and then afterwards we added the concentrated alkaline medium. The reason why we add a small amount of acid before we add the potassium hydroxide was to have a neutralization reaction happening in this medium so that it releases a small amount of energy. When the small amount of sulfuric acid that was added into this medium comes into contact with the concentrated potassium hydroxide, a small neutralization reaction will happen. This will increase the temperature of the medium because neutralization reactions are exothermic. They will release some energy, and due to the release of this energy, this medium will heat up, and that energy will be used to convert permanganate anions into manganate anions. So this chemical reaction or this conversion requires a little bit of energy, and that will be provided due to the neutralization reaction that is taking place after we added some amount of sulfuric acid. So first of all, you have to keep in mind when it comes to permanganate ions, we have 7 or +7 oxidation state in manganese, and manganate ions contain +6 oxidation state in manganese. And this conversion happens in alkaline medium. And later on, we move on to taking the manganate ion medium, which is an alkaline solution at this point, because we discussed earlier on as well that manganate ions are stable in highly alkaline medium. So if you take manganate ions and react it with hydrogen peroxide, we can convert these manganate ions into manganese dioxide, which we have over here. Manganese dioxide is a brown color precipitate that you form over here. And the oxidation state of manganese in manganese dioxide was +4. Now, all of these reactions up until this point was done in alkaline medium. And we can see oxidation state of manganese in permanganate anion, or +7 oxidation state of manganese, can be brought down all the way up to +4 oxidation state in alkaline medium. However, you cannot bring it further down into +2 oxidation state in alkaline medium. In alkaline medium, we have oxidation state reduced only up to +4 oxidation state, which means whenever you are conducting an experiment where you have potassium permanganate, and if you are trying to reduce the oxidation state of potassium permanganate, you can only bring it down to +4 oxidation state, which is manganese dioxide. After observing that, we can move on to take a look at what happens in acidic mediums. So if you take manganese dioxide and add concentrated hydrochloric acid, we can see the +4 oxidation state of manganese dioxide was brought all the way down to +2 oxidation state. So in acidic medium, students, we can bring down the +7 oxidation state of manganese all the way down to +2 oxidation state of manganese. So potassium permanganate or permanganate anions +7 oxidation state can be brought down all the way down to +2 oxidation state in acidic medium. This, however, is not possible in alkaline medium. In alkaline medium, we can bring it all the way down to +4, but not up to +2. So we have made a note of it as well over here. As indicated above, in acidic medium, the higher oxidation states of manganese can be reduced or brought down to +2 oxidation state of manganese, which is Mn2+. In alkaline medium, the higher oxidation states have reduced only up to MnO2 or manganese dioxide, which has an oxidation state of +4. This is something that is important that you should keep in mind when conducting this experiment. Now, let's move on to an additional reaction that is not present in the practical. So we saw earlier on when we converted potassium permanganate into potassium manganate was stable in highly alkaline medium. And we even discussed if you added a little bit of water or if you add acid into this potassium manganate solution, it will undergo a chemical reaction. And what we are going to observe over here is what actually happens. Upon addition of water and then diluting the alkaline medium, or upon addition of acid and trying to neutralize some of the base that is present in the medium, what happens is the manganate anion undergoes a disproportionation reaction, producing permanganate anion, which is purple in color, and manganese dioxide, which is brown in color. Now, students, if you observe over here very clearly, you would notice the oxidation state of manganese in MnO4 2- or oxidation state of manganate anion is +6, and the oxidation state of permanganate anion or manganese in the permanganate anion is +7. Over here, when it comes to manganese dioxide, the oxidation state there is +4. So now we can clearly see that oxidation state of manganate has a +6 oxidation state, and it has gotten oxidized into +7, and it has also gotten reduced to +4. So an oxidation and a reduction has happened to the same chemical species, which is our manganate ion. This indicates, students, that this particular reaction is a disproportionation reaction. Any reaction where the same chemical species is undergoing oxidation as well as reduction is known as a disproportionation reaction. So what we have here is a disproportionation reaction. Now, this disproportionation reaction can take place when you add a small amount of acid or when you add water. So this chemical equation can be written with H+ or as well as with water. Let me erase these notes over here. Now, students, you can very clearly see what the observations are. Earlier on, we had some written text here, which was not allowing us to properly observe the colors. So over here, what you have is potassium manganate turning into potassium permanganate, which is purple in color. And at the same time, due to the disproportionation reaction that is happening, we will be producing a brown color manganese dioxide precipitate. And they are not obviously going to be in two separate test tubes like indicated in this diagram. Now in this diagram we have separately indicated it so that you understand what the products are. However, this is going to be made in the same test tube. You can see purple color supernatant with brown color precipitate. This precipitate is going to be brown in color, and the supernatant or liquid lying above the precipitate is going to be purple in color. So it's a combination of these two test tubes that you're going to be observing in this chemical reaction. Now what you have here is the same chemical reaction happening when you are diluting it with water. So you can very clearly observe the oxidation number change over here when you add water to a potassium manganate solution, which is highly alkaline, which is present in a highly alkaline medium. You're going to see the potassium manganate or manganate anion goes from +6 oxidation state to +7 oxidation state, which is going to be an oxidation. And at the same time, it goes from +6 oxidation state to a +4 oxidation state, which is going to be a reduction. So students, this reduction is from +6 to +4, which involves release of or take up of 2 electrons, and the oxidation goes from +6 to +7, which means the take up of 1 electron. So over here, 2 of our manganate anions convert into 2 permanganate anions, releasing 2 electrons. So therefore, this has to be multiplied by 2, meaning the oxidation reaction happens twice when the reduction reaction is happening once, so that the number of electrons that are released are going to be a match with the number of electrons that are taken in when it comes to the reduction reaction. So we can see you have 2 permanganate ions. Out of the 3 manganate ions, 2 of them actually converts into permanganate, as the oxidation reaction happens twice, and 1 permanganate and 1 manganate ion is going to convert into manganese dioxide, conducting a reduction reaction. And this is the overall reaction when we add water to highly alkaline medium containing potassium manganate, which is a green color solution, and the final observation would be the production of a purple color solution along with a brown color precipitate. So in the reaction above, they say the manganate ions oxidizes to form permanganate ions. It is observed that manganate ion is also reduced to form manganese dioxide. Same chemical species, oxidizing and reducing. This indicates that manganate ions undergoes both oxidation and reduction, makes this reaction what is referred to as a disproportionation reaction. So this reaction is also quite important, students. Although this is not tested in the lab, you should keep this in mind when you're diluting a potassium manganate solution present in an alkaline medium. What happens is the potassium manganate will undergo disproportionation, forming potassium permanganate solution and manganese dioxide. Or the same result can be obtained when you add a little bit of dilute hydrochloric acid or any dilute acid and try to neutralize the alkaline medium. At that point, you would observe the manganate ions giving us a permanganate ion and manganese dioxide. So the same observation can be obtained by diluting the medium or by adding dilute acid to the medium. Now, students, we have discussed all of the theory parts revolving around the experiment number 22. All that is left for us to do is going and observing these chemical reactions happening in the laboratory. So let's move on to the lab and conduct this experiment. Students, today we'll be looking at Chemistry Practical 22. In this practical, we'll be speaking of different oxidation numbers of manganese compounds. So here in this practical, we'll be starting with potassium permanganate, where the oxidation number of manganese is +7, and then we'll be reacting it with different reagents and converting the oxidation number of manganese +7 to +6, then to +4, and later on to +2. And along the way, we will be discussing the colors we observe of these compounds. So let's move on to the reagents that we need for this practical. Let's take a look at the reagents we will be using for this practical. We have here potassium permanganate, KMnO4, and we have here sodium hydroxide solid pellets. We will be using them instead of concentrated sodium hydroxide because we need the reaction to kind of take place in a highly alkaline medium, and this is more suited than using concentrated sodium hydroxide solution because we can see the color change faster when we use them. Over here we have concentrated hydrochloric acid, we have dilute sulfuric acid. Over here we have hydrogen peroxide. We have made a dilute hydrogen peroxide solution as well. We have it here in a boiling tube. So these are the reagents that we will be using for this practical. Let's move on to the practical. First, we need to make a potassium permanganate aqueous solution. We have potassium permanganate solid over here. If you want to observe the color, you can see that the potassium permanganate solid is a deep purple color solid. Now I will be taking a little bit of potassium permanganate into a boiling tube. I'll add a little bit more. Now I will be using a wash bottle with distilled water in it, and I'll be adding a little bit of distilled water to dissolve this potassium permanganate solid. To show you the color, I'll have to dilute this quite a bit. So this is a very concentrated potassium permanganate solution. You can see a very deep purple color will be observed over here. So let me dilute it a little bit so that we can see the color change a bit more clearly. So I'll be transferring a little bit of this solution onto a different beaker. And then I will be adding water until I see a little bit of a lighter color in potassium permanganate solution. So over here you can see a bit of a lighter color, but even this is still quite concentrated. I will have to dilute it a little further. Now we will work with this purple color solution, which is a dilute potassium permanganate solution. Firstly, we have to observe the oxidation number of potassium permanganate. In this potassium permanganate or KMnO4 solution, the manganese is at +7 oxidation state. We need to convert it to +6. So in this case, we will be using dilute sulfuric acid and concentrated sodium hydroxide. So the way in which we obtain concentrated sodium hydroxide is by addition of sodium hydroxide pellets. First of all, let us add the sodium hydroxide pellets into this. To do that, I will be using the test tube rack here. You can see me transferring a little bit of sodium hydroxide pellets into the potassium permanganate solution. Then I'm going to try to dissolve it as much as I possibly can. While doing so, I'm going to add a little bit of sulfuric acid. Now, when we keep on swirling this around, we are supposed to see the sodium hydroxide pellets dissolving, and as it dissolves, the color of the potassium permanganate should change from purple to a green color, because we are going to be forming potassium manganate, which is green in color. So let's see if we can get to that observation. We would need a little bit more sodium hydroxide, as it seems. So we will add a little bit more sodium hydroxide into this. We can see the color of potassium permanganate is slightly changing into a little bit of a green color. So it's still purple, but you can see the purple color fading a little bit. As the reaction takes place, you will see the disappearance of the purple color more clearly. Now we are seeing that the purple color is completely not there anymore, and we are very clearly seeing a green color. Let me swirl it a little bit more and then show you the color very clearly. Let's compare it against the white background. Now you can see that we have formed a green color solution. This green color solution contains potassium manganate, K2MnO4. So in a K2MnO4 solution, the manganese is at the oxidation number +6. We had potassium permanganate, KMnO4, which had an oxidation number of +7 and was purple in color. We saw it over here. Now we have potassium manganate, K2MnO4, which is green in color. Let's dilute this solution a little bit, as we need to transfer a little amount of this K2MnO4 solution into a different test tube. so that we can treat it with hydrogen peroxide. So I have taken a little bit of potassium manganate, and now I will be using hydrogen peroxide and converting this potassium manganate into MnO2, manganese dioxide. So we have our hydrogen peroxide here. We have made a dilute hydrogen peroxide solution earlier on, and we have it over here. So let's add hydrogen peroxide into our potassium manganate. We can see upon addition of hydrogen peroxide, the green color of the potassium manganate completely disappeared, and now it is appearing brown. Let me compare it against a white background. You see a brown color in this boiling tube at this moment. Here, don't assume that we have formed a solution. This is not a solution. What you have formed here is MnO2, which is insoluble in water, and it is a precipitate that is formed. However, MnO2, manganese dioxide, is formed as really fine particles. So these really fine solid particles are suspended in water, making it look as if it was a solution, but it is not. So the color is what you should observe here. We converted the green color potassium manganate into manganese dioxide, which is brown in color. So what is the oxidation state over here in manganese? So in MnO2, the oxidation number of manganese would be +4. We have manganese at +4 oxidation state. Let's take another boiling tube and transfer some of this manganese dioxide into that other test tube. I will dilute this test tube a little bit, dilute this solution a little bit by adding some water. You can see the brown color still persists. So after diluting a little bit, I am going to be adding concentrated hydrochloric acid. Upon addition of concentrated hydrochloric acid, we are expecting to see that this brown color disappear. So upon addition of hydrochloric acid, concentrated hydrochloric acid, MnO2 will get converted into Mn2+ ions, and it should form a colorless solution. As you can see, upon addition of very small amount of concentrated hydrochloric acid, we formed a colorless solution because the MnO2 converted into Mn2+ upon addition of concentrated HCl. Manganese ions or Mn2+ ions are considered to be light pink in color. However, we would not make this observation if the concentration of Mn2+ ions in the solution is very small. So we have a very dilute Mn2+ concentration here. Because of that, we will not observe that light pink hue. Instead, we observe the color to be colorless. In most cases,
When it comes to Mn2 plus ion solutions, we will make this colorless observation, although Mn2 plus is going to have a pink color hue when they are in really high concentrations. So in summary, let's take a look at what we did in this experiment. In summary, in this practical, we wanted to see the different oxidation states of manganese. So we started with potassium permanganate. Potassium permanganate, or KMnO4, is a purple color solution when you dissolve potassium permanganate solid in water. So we made the observation when potassium permanganate KMnO4 is dissolved in water, it is purple in color. Oxidation state of manganese over here is +7. We took a little bit of potassium permanganate, purple color solution, and we added potassium hydroxide. In this case, we actually added sodium hydroxide and dilute sulfuric acid, and we converted the potassium permanganate to potassium manganate. Potassium manganate is green in color, or in other words, the formula of potassium manganate is K2MnO4, which is a green color solution. Over here, the oxidation state of manganese is going to be +6. And then we took +6 potassium manganate and treated it with some hydrogen peroxide. So when you treat it with hydrogen peroxide, you can see the color of potassium manganate completely changed, and we formed a brown color manganese dioxide, MnO2. MnO2 is insoluble in water, so what we have formed here is a precipitate. But since we have formed a very fine precipitate here, it is suspended in water, making it look as if it was a solution. So the oxidation state of manganese here in MnO2 is going to be +4. Then we took MnO2 into another boiling tube, and we treated it with concentrated hydrochloric acid. At that point, the manganese dioxide dissolved in concentrated hydrochloric acid, forming a colorless solution. In this colorless solution, what you have here is Mn2 plus ions. And the oxidation number of Mn2 plus, as you may have already guessed, is +2. And I told you earlier as well, Mn2 plus ions are perceived to be pink in color. However, in low concentrations, Mn2 plus is going to appear colorless. So that is all for this practical. All of the more important theory parts revolving around this practical and the questions related to this practical will be discussed in our next session.
Students, in the previous part of this practical, we had a look at the theory revolving around the chemistry of manganese, and then we went into the labs, and then we conducted an experiment exploring different oxidation states of manganese, such as +2, +4, +6, and +7. And now we are going to be looking at the past paper questions that are connected to the chemistry of manganese. So in this particular session, we aim to improve your knowledge about the chemistry revolving around manganese, and we are going to give you necessary knowledge as to how you should answer questions that are related to the chemistry of manganese. So let's move on to our first question. So over here we have a very simple question. They say M is a D block element. M is a D block element. So that is a very important
statement, so that we know we are dealing with an element that is present in D block, and its highest oxidation state is observed in the ion MO4 minus. So M is a D block element and its highest oxidation state is observed in this particular ion. And then they ask you to write the full electronic configuration of M and identify M. So these are, again, hopefully by the time that you answer the first question, you know the identity of M already. And then write M's most stable oxidation state in aqueous medium. Write the necessary reagents and conditions needed to convert the previous state that we have identified, the most stable state of M, or most stable oxidation state of M, to MO4 minus. So you have to convert the oxidation state that we have mentioned in question 3 to MO4 minus ions, and they're asking for the conditions that are required for that reaction. Now let's find out the answers to the first question. So the very first question that they say, that they ask, is write the full electronic configuration of M. So before doing so, we need to figure out what M might be. So we have MO4 minus, and they say at this point, or in this ion, M has its highest oxidation state. Let's say the oxidation state of M in this ion is X. So then we can write an expression, X plus the oxidation state of oxygen is -2 in this compound, and there are 4 oxygens. So therefore 4 into -2 is equal to the overall charge of the ion, and the overall charge of the ion is -1. So X minus 8 is equal to -1. At this point, you can find out the value of X to be +7. So the highest oxidation state of this specific element that they're talking about is +7. So then we need to figure out in the D block of elements which element has its highest oxidation state at +7. So if you write down the elements in our D block, we have scandium, we have titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Now, if you observe the oxidation states of each of these D block elements, let's talk about the highest oxidation states of each of these D block elements. We are going to note that scandium has a highest oxidation state of +3, and titanium has highest oxidation state of +4, vanadium +5, chromium +6, and manganese +7. So over here we have found our answer. We have manganese with its highest oxidation state at +7, and the question says the D block element that they have named M has its highest oxidation state at +7 as well. So therefore we can identify that the element that we are actually dealing with is none other than manganese. So the element that they're referring to as M is manganese. Now Let's move on to the question they're actually asking. That is, write the full electron configuration of M. So if you take a look at manganese, you would know manganese is the 25th element in the periodic table, or in other words, the atomic number of manganese is 25. So manganese should have 25 electrons in it. So let's fill these 25 electrons into its proper electronic configuration. You have 1s2, 2s2, 2p6, 3s2, 3p6. By now, we have filled most of our electrons here, and we have 7 more electrons to fill. So most of you will start filling it after 3p6. You have to fill electrons to 4s2, and then you would write it as 3d5. However, some of you will rearrange it in the following manner, where you write 3d5 before writing 4s2. Actually, that is also correct. Majority of the time, that is how we keep our answer. So you can write it as 1s2, 2s2, 2p6, 3s2, 3p6. Then after that, before filling electrons, or we know actually 4s2 electrons are filled first, but we can keep 3d5 with all of the other 3 subshells. So we can keep 3s, 3p and 3d subshells together because they are present in one quantum shell. However, both of these forms of the answer is correct. You will gain a mark for both of these forms of the answer. Now, let's move on to the next question, which is identify M. So M is already identified because we do know the identity of M is manganese. So you can write manganese using the symbol, or else you can write it in words. If you write manganese without writing the symbol, that is also correct. In the next part, for the asking is the most stable oxidation state of M in aqueous medium. What is the most stable oxidation state of M in aqueous medium? Students, manganese has the most stable oxidation state at +2, and it forms Mn2 plus ion, which has +2 oxidation state. So the answer to this question, when they ask what is the most stable oxidation state of manganese in aqueous medium, it is +2. And the chemical species that it forms at that oxidation state is Mn2 plus ions. And we come to this question, where they ask us to convert MO4 minus to Mn2 plus. Basically, we know MO4 minus is MnO4 minus, or permanganate ion, and they're asking us to convert the permanganate ion to Mn2 plus ion. In this situation, students, what is taking place is this: MnO4 1 minus. So first of all, we have to identify that we have to write this down, where M is basically Mn, and therefore MO4 minus is MnO4 minus.
And the state that they ask us to convert it to is Mn2 plus. So the oxidation state of manganese over here is +7, and over here it is +2. And as you can see, this is a reduction. Now, to carry out this reduction, you would need reducing agents. Or as we can say, permanganate ion is acting as an oxidizing agent. However, permanganate ions turn into Mn2 plus in acidic medium. In alkaline medium, it will turn into MnO2, which is a brown color precipitate. So before we start anything, you have to keep in mind that this transformation should happen in acidic medium. And then we can take different types of options here to carry out this transformation. We can have, if you take MnO4 minus, we can convert it into Mn2 plus using a few different reagents. So I will write a few down over here. Nonetheless, you have to use dilute acidic medium. So we can use dilute sulfuric. And one of the reagents you can use is Fe2 plus. Fe2 plus, or we can say ferrous. So when you use Fe2 plus, we are converting Fe2 plus. Now this MnO4 is reducing to Mn2 plus, and Fe2 plus is getting oxidized to Fe3 plus, and manganese 2 plus will be formed, converting permanganate ions into manganese 2 plus ions. The other option we have is sulfur dioxide. If you use sulfur dioxide in acidic medium, you can see sulfur dioxide getting converted into sulfate ions. Again, you can see manganese is formed from permanganate ions. So permanganate ions get reduced, whereas sulfur dioxide or sulfur in sulfur dioxide gets oxidized. So over here, the oxidation number of sulfur is +4, and when it comes to sulfate, the oxidation number of sulfur is +6. So therefore, that is an oxidation. And we have potassium iodide. If you add potassium iodide in dilute sulfuric acidic medium, you will be able to produce I2 and Mn2 plus. Again, iodide ions getting converted into I2 is a change of oxidation number of iodine from -1 to 0. So it's an oxidation, whereas permanganate ions undergo a reduction. And the next option is to use H2O2. Now, H2O2, when reacted with permanganate ions, we will produce Mn2 plus again over here, meaning MnO4 has reduced in its oxidation number, and oxygen over here in hydrogen peroxide is in -1, so it has to be oxidized to O2. So from -1 to 0, oxygen has gotten oxidized, whereas permanganate ion has gotten reduced from +7 to +2. So you can use either one of these
reagents to get to your final answer. So we don't have to write all 4. We can actually use one of these answers, right? So we can say to carry out this transformation, we can use H2SO4 or dilute H2SO4 and Fe2 plus. Or else if you have written dilute H2SO4 and ferrous sulfate, that is also correct. If you wish to include the other answers as well, you can write them as dilute H2SO4 and potassium iodide, dilute H2SO4 and sulfur dioxide, or dilute H2SO4 and hydrogen peroxide. And now they're asking us to write one important use of manganese, or M in this case. We use manganese quite a lot for forming different alloys. So when it comes to even manufacturing of steel, manganese is used to form that specific alloy. So the use of manganese is producing alloys. Right. With that, let's move on to our next question. In this second question, we are asked if the first statement is true or false, and if the second statement is supporting the first statement, and if it is true or false as well. So you find these kind of questions towards the latter part of your MCQ paper. So I'm sure you are familiar with questions of this nature. So let's dive into the question and see what the answer for this question is. So the very first statement is telling us that the aqueous solution of zinc 2 plus and Mn2 plus ions acidified with dilute hydrochloric acid will not, that is important, will not form precipitates when reacted with H2S. So that is a very first statement. So you have solutions of zinc 2 plus and Mn2 plus, and they're acidified with HCl. And we are reacting it with hydrogen sulfide. Would you see a precipitate? So to answer this, we have to move to qualitative inorganic analysis. So in the analysis group 4, we'll take it over here. In our, let's say, analysis group 2 actually. In analytical group 2, you have the following ions reacting with H2S in acidic medium. Stannous. Now these ions are normally found in the lower parts of group 14. Stannic and lead. And there are some ions found in group 15 are also taken. Group 15, the lower parts of group 15, you find arsenic, antimony, and bismuth. And we have cadmium, mercury, and copper as well in analytical group 2. When it comes to these ions, they react with H2S in acidic medium. So we have dilute HCl, and we are reacting these elements or these ions in with H2S in acidic medium. So when you react these metal ions with H2S in acidic medium, you end up forming insoluble metal sulfides. So this is how we identify whether these elements are present in aqueous medium. When it comes to analytical group 2, we add dilute hydrochloric acid to acidify the medium and then add H2S. These ions that we have mentioned over here has a very low solubility product when it comes to their metal sulfide. So in other words, the KSP of metal sulfides of these ions are extremely low. So therefore, even with a small amount of sulfide ions in the medium, these ions will precipitate out as metal sulfides. So that is why we use these elements in analytical group 2, and we identify the presence of them with the use of acidified hydrogen sulfide. So in this group, you do not see manganese 2 plus or zinc 2 plus, meaning the first statement is correct, right? In an acidified medium, when you react manganese 2 plus or zinc 2 plus with H2S, it does not form water insoluble metal sulfides. So therefore, the first statement is correct. The first statement that we have over here is correct because we are talking about reacting zinc 2 plus and Mn 2 plus in acidic medium with H2S, and they are saying they are not producing, this is the most important part, they are not producing precipitates, which is correct. Only the elements, rather only these ions that are mentioned here will be producing insoluble metal sulfides in acidic medium when reacted with H2S. But at the same time, students, we can look at analytical group 4 as well. So if you take a look at analytical group 4, let's take a look at the analytical group 4. If you take a look at analytical group 4, we have elements like manganese 2 plus, cobalt 2 plus, nickel 2 plus, and zinc 2 plus. These elements will react with H2S in alkaline medium and form insoluble metal sulfides. So when it comes to group 4, analytical group 4, we see these metal ions forming insoluble metal sulfides with H2S when they are reacted in alkaline medium. So what is the reason for these metal ions to precipitate out in the fourth group and not in the second? As you remember, in the second analytical group, we added dilute HCl and then reacted with H2S. Hydrogen sulfide do not fully dissociate in water. Hydrogen sulfide do not fully dissociate in water. It normally dissociates in the following manner. It happens in 2 steps, but let's write it in a single step over here for convenience. So H2S dissociates partially in water and produces a small amount of sulfide ions. Earlier, I mentioned the ions that are present in analytical group 2 are having a very small solubility product or KSP when it comes to their metal sulfides, meaning even a small amount of sulfide ions in the medium will be able to precipitate out those ions as insoluble metal sulfides. Over here, we can see if you have H plus in the medium, or if you have added dilute HCl into the medium, what happens? The H plus concentration of the equilibrium will go up, making this equilibrium position to shift towards the left-hand side. So therefore, the sulfide ion concentration in the medium will go down quite a lot. So therefore, in acidic medium, the sulfide ion concentration is quite low. This is the condition in analytical group 2. Even in low sulfide ion concentrations, the metal ions present in analytical group 2 are capable of forming insoluble metal sulfides, and they will precipitate out from the medium. When it comes to the ions that are present in analytical group 4, such as zinc, manganese, cobalt, nickel, these ions do possess a little bit of a higher KSP value, indicating they have a little bit of a higher solubility for their metal sulfides. So they do not make precipitates when the sulfide ion concentration is very low. They do, however, form precipitate if the sulfide ion concentration in the medium is higher. Now, keep in mind, when it comes to group 4, we made the medium alkaline by adding ammonium hydroxide. Ammonium hydroxide in the medium releases OH minus ions into the medium, which can react with the H plus in the medium. These OH minus ions that are released into the medium can react with the H plus ions in the medium and form H2O. So students, when the OH minus ion concentration goes up, as H plus reacts with OH minus, the H plus concentration will come down. As the system will always try to resist change, the equilibrium position of this equilibrium will shift to the right-hand side, producing more and more of these products. So this will cause the sulfide ion concentration to go up. So in the group 4, what we are trying to do is, we are trying to increase the sulfide ion concentration by reacting the metal ions that are in group 4 in alkaline medium. So in alkaline medium, as you can see, the sulfide ion concentration is quite high, and therefore when these metal ions come into contact with those kind of high concentrations of sulfide ions, they will precipitate out as metal sulfides. So keep in mind, the metal ions in group 4 did not precipitate out in group 2, analytical group 2, because their KSP, their solubility product, was a bit higher than the ions that are found in analytical group 2. So therefore, they needed a higher concentration of sulfide to make metal sulfide precipitate. So we were here at this point. You can see that the first statement is correct. However, the second statement, let's take a look at that, whether the second statement is correct as well. Zinc sulfide and manganese sulfide are soluble in HCl. So is it true? Yes, this is true. Both of these are soluble in HCl. If you take zinc sulfide and manganese sulfide, they will easily dissolve in HCl and form solutions. So this statement is true. However, does it explain the first statement? Not really. So for this particular question, the answer is the first statement is true and the second one is also true. However, it does not explain the first statement. So that is how you would get to the answer for this question, and let's move on to the next one. Now, let's take a look at the third question. In this third question, we are going to see that when it comes to certain questions revolving around manganese, we see a little bit of a repetition, right? This is 2008 A-level question. You can see they're asking quite similar questions to what we discussed in the first question. So M is a 3D transition element. M is a 3D transition element and its highest oxidation state is +7. So we saw in the very first question we did as well, they mentioned that there's an element called M in 3D or in the D block, and they mentioned that the highest oxidation state of M was +7. But in that question, they were not this direct. They gave us an ion and we had to find the oxidation state of M there. However, this directly tells us the oxidation state, the highest oxidation state of M is +7. So since we have done the question number 1, we know what this element is. This element is manganese. So they're asking us to identify M. We have already done a similar question. So we have an understanding. +7 highest oxidation state is seen in manganese. Write M's full electronic configuration. Write the chemical formula of M's most stable oxidation state and mention its color. So let's move on to the first part. So the answer to this question is identify M. M is going to be manganese. Why? Because the highest oxidation state of manganese is +7, and this question asks for a 3D element or D block element that has its highest oxidation state as +7. So after that, we can actually move on to the next question, which is M's full electronic configuration. By now, you must be very familiar with M's full electronic configuration. So in this case, we know M is Mn or manganese. It's going to be 1s2. Manganese is 25th element. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, and 4s2. Altogether, if you count here, we have 25 electrons present here. And now we move on to our next question, which is asking us to write the chemical formula of M's most stable oxidation state and mention its color. Again, we saw this earlier as well. M's most stable oxidation state is going to be +2, and it is seen in Mn2+ ion. In the aqueous medium, Mn2+ aqueous ion, or in the aqueous medium, it will have a pale pink color. In the practical itself, I hope you remember in the previous session, we saw pale pink color of manganese is not very easy to observe. However, the color of Mn2 plus is going to be pale pink in color. At the same time, if you take it a step further, apart from this question, just for us to know, what is the most stable oxide that manganese forms? So the most stable oxide the manganese forms is MnO2, right? So the most stable oxide that manganese forms is MnO2. At this point, the oxidation state of manganese is going to be +4, right? +4 is the oxidation state of manganese, and the color of MnO2. Actually, MnO2 is a water insoluble oxide, and it is going to have a really dark brown color to its precipitate, right? So we can say it's dark brown. You can even go to the point of saying blackish brown or extremely dark brown color precipitate will be formed. And even the formation of this dark brown precipitate was observed in our experiment. Right, so now here we can take the time to remember a few other details as well. In addition to these two, let's remember some of the other oxidation states of manganese as well. Now we saw +2 and +4 oxidation states of manganese, and now let's remind ourselves of some other oxidation states of manganese here as well. We saw in acidic medium we can have manganese in +7 oxidation state forming permanganate iron. So permanganate iron has a color which is purple. Permanganate ions are purple in color and has an oxidation state of +7 and is observed in acidic medium. And when it comes to manganate ions are observed in extremely alkaline medium, and the oxidation state of manganate ions or manganese in the manganate ion is going to be +6. So +6 oxidation state is observed in manganate iron, and the manganate ion is going to be green in color. So we have a few oxidation states observed here. We spoke about the most stable oxidation state in aqueous medium, pale pink color Mn2 plus ions, and we have the most stable oxide of manganese, which is MnO2, which has oxidation state of +4, and the color is a dark brown. And we looked at permanganate ions, which are normally stable in acidic medium, and permanganate ions are going to be having an oxidation state of +7 and they are purple in color. Finally, we came across manganate ions, which are normally stable in extremely alkaline mediums, and they are going to be having an oxidation state of +6 and they are green in color. So keep these details in mind if you want to improve your answering skills when it comes to questions revolving around manganese. Students, let's take a look at our fourth question. They say Y is an inorganic covalent compound. So that itself, one thing is clear to us. This is not an ionic compound, it's a covalent compound, indicating that there aren't any positive or negatively charged ions here. So we can be very sure that it doesn't have any metal ions. Having metal ions, or any ion for that matter, will result in an ionic compound, and here what we have is a covalent compound. And the molar mass, they say, is less than 40. Obviously, if you take any, now we were talking about D block elements, any D block element will have a molar mass or atomic mass for that matter, which is greater than 40. So here, if it is smaller than 40, that means it's definitely not including any 3D elements. And why is aqueous solution undergoes the reactions below? It decolorizes acidified potassium permanganate while releasing O2. So acidified potassium permanganate is purple in color and it becomes colorless. So you see, when it comes to potassium permanganate, when it reacts in the acidic medium, it can turn to Mn2+, which is pale pink in color. However, like I mentioned in the beginning of this practical, Mn2+ aqueous ions are considered to be colorless because their color intensity is not that high. Although it is mentioned pale pink in color, it is not going to be observed when you're carrying out the reaction. So it's going to appear as if the purple color of potassium permanganate disappears. So we can identify that potassium permanganate is turning into Mn2+. And it is releasing, so whatever the compound Y that was reacting over here was capable of releasing oxygen as well. And then over here we have potassium permanganate in alkaline medium reacting with Y and releasing oxygen. So students, again, we can see release of oxygen. This is a clear indication that it contains oxygen. At the same time, we can see a brown color precipitate is being formed over here. So potassium permanganate, when reacting in alkaline medium, if it is getting reduced, it will turn into MnO2. MnO2 or manganese dioxide is a brown color precipitate. So that is why you can see in this case MnO4 minus or potassium permanganate is forming a brown color precipitate. So we can be sure that the brown color precipitate is manganese dioxide. So in each of these cases, in A and B both, we saw the potassium permanganate underwent a reduction. When it comes to A, it went from +7 state to Mn2+, which is at +2 state. When it comes to the second reaction, we saw potassium permanganate in +7 oxidation state, and it goes to MnO2, which is in +4 oxidation state. So all of them were reductions. And the C reaction is a little bit different to that. They say Y reacts with colorless sodium bromide and forms a yellow color solution. So the solution was colorless initially, but after reacting with Y, we see sodium bromide or the solution turns to a yellow color. Why might this be? In this medium, in sodium and bromine, sodium ions are definitely colorless, and so is bromide ions. However, if bromide ions undergo oxidation to turn into bromine, bromine in aqueous medium will be having a color, and that color is going to range from yellow to orange depending on the concentration of bromine that is present in aqueous medium. So if you have a low amount of bromine in water, then you're going to see a yellow color solution being formed. So we can see here bromide ions in the medium went from 1- oxidation state to 0 oxidation state. So this is an oxidation, meaning the Y that we see over here is carrying out an oxidizing, meaning the Y that we see here is acting as an oxidizing agent. And in the previous reactions, since potassium permanganate underwent a reduction, we can say the Y was acting as a reducing agent. So this is a clear indication, whatever the compound Y might be, it is capable of both oxidizing and reducing. And then we have the next statement, which is going to give you a bit of a clearer idea about what this compound might be. They say Y decomposes slowly at room temperature and decomposes faster in the UV radiation. They say Y decomposes slowly at room temperature and decomposes faster under UV radiation. So this sounds like a familiar compound by now. We have a few criteria to be met. It has to have a molar mass less than 40 grams per mole. And at the same time, it should be able to get oxidized and reduced at the same time. And at the same time, we have a compound that is getting decomposed when exposed to UV light or even at room temperature, a compound that decomposes. Hydrogen peroxide ticks all of these boxes. Even in the lab, hydrogen peroxide is normally stored in a brown color reagent bottle to make sure that UV radiation, or that it is not exposed to UV radiation. Or in the presence of even light, we know hydrogen peroxide's decomposition is somewhat increased. So therefore, we might be very familiar with hydrogen peroxide being able to decompose in the presence of UV radiation. So this point will very clearly indicate what the compound you're dealing with is. So after figuring out, or after having an idea that this is hydrogen peroxide, we can then move on to writing equations for each of these reactions, but that question is asked in a separate area over here. So when we get to that point, we will complete that part. And then we have another very interesting point, which is, they say when oil paintings are exposed to air polluted with H2S, basically when oil paintings get exposed to H2S, we are going to see the white color pigments that are made with lead carbonate turn black due to formation of lead sulfide. So lead carbonate is white, and when it comes into contact with hydrogen sulfide, it turns into lead sulfide, which is a black color pigment. If you want to convert it back into a white color pigment, you can do so by exposing it to the Y compound. So Y compound will convert it back to a white color pigment. So the very first question that they ask after giving us this information is this: identify Y. So as I mentioned earlier, Y is hydrogen peroxide. It ticks all of the boxes, right? It has to have a mass of less than 40. So if you quickly calculate the mass over here, there are 2 hydrogens, meaning it's going to bring in a mass of 2 here. There are 2 oxygens. It's going to bring in a mass of 32. So it is right under 40, which is going to be 34. So the mass of hydrogen peroxide is 34. And at the same time, it's a inorganic covalent compound. And it is capable of both oxidizing and getting reduced. Hydrogen peroxide can get oxidized to form oxygen gas, or else it can reduce to form water. So therefore, hydrogen peroxide can act as both an oxidizing agent and as a reducing agent. So the hydrogen peroxide is now identified. Over here, they ask you to draw the dot cross structure of hydrogen peroxide. So when you're trying to draw the dot and the cross structure, first of all, we can start writing how atoms are present in the hydrogen peroxide molecule, like this. So the first hydrogen, let's indicate its electrons as a dot, and then you can see there's a bond between hydrogen and oxygen. So therefore, there's going to be an electron coming in from oxygen over here, forming the oxygen and hydrogen bond. And normally, when it comes to a dot cross structure, we indicate the outermost electrons of a given atom. So oxygen has 6 outer electrons, and 2 of the electrons are going to be present as unpaired electrons. The other 4 are present as paired electrons. So one of the unpaired electrons of oxygen is now paired with hydrogen over here, and then we have adjacent oxygen atom that is going to be indicated. Electrons of the adjacent oxygen atom is going to be indicated with dots. Now you can see the bond between the 2 oxygens over here is present as a dot and a cross here, and the other unpaired electron are indicated over here with a dot, and the paired electrons can be indicated this way. Finally, the final electron that is coming from hydrogen can be indicated with a cross. Now students, something to keep in mind is whenever you are trying to draw an atom's Lewis dot structure or dot cross structure. So Lewis structure and dot cross structure is different. However, if you're trying to draw the dot cross structure for a given atom, keep in mind you're only going to represent the outermost quantum shell electrons of a given atom. Oxygen has 6, so therefore you have to indicate 6 electrons around oxygen. And when you're drawing it, you have to draw it by placing electrons. Let's indicate electrons by x's. 1 electron in each side, and then after you are done adding an electron to the 4 different sides around an atom, then you can start pairing the electrons up until the total number of electrons in the outermost quantum shell is represented around the atom. So when you're starting to draw it, don't start by pairing it up, right? Don't start it like this: 1 2 3 4 5 6. If you draw it like this, you'll see when it comes to oxygen, you do not indicate the presence of any unpaired electrons. So therefore, drawing it right like that would be incorrect. Right, while keeping that in mind, let's move on to our next slide. Over here, they're asking us to draw the shape of Y. So students, when it comes to drawing the shape of hydrogen peroxide, if you take a look at the electron pair arrangement around oxygen, you're going to see a pair of electrons between the hydrogen atom and the oxygen atom, and again oxygen atom and the second oxygen atom that is present in the hydrogen peroxide molecule, and there will be 2 lone pairs around oxygen as well. So around oxygen, there's basically 4 electron pairs. 2 of them are bond pairs and the other 2 are lone pairs. And if you are drawing the electron pair geometry or the arrangement of electron pairs, you are going to see a tetrahedral arrangement around each oxygen atom. So therefore, the final structure would look like this. So students, this is how the electron pairs are arranged around oxygen. However, when you're trying to answer this question and when you're trying to draw the shape of hydrogen peroxide, keep in mind this is how you are expected to draw this shape. So the hydrogen peroxide has 2 oxygen atoms and 2 hydrogen atoms. The 2 oxygen atoms are going to be present in between 2 planes, and the hydrogen atom, if you draw it like this, you can very clearly see the hydrogen atoms are going to be present in 2 different planes. So it's, if you take this plane is present somewhat vertically, the other plane will be present flat on the ground, right? So there's an angle between the 2 planes over here, and that angle is, this angle is going to be 111.5, and the angle between oxygen hydrogen bond and oxygen oxygen bond is going to be 94.8 degrees. Right, so this is how you would draw your hydrogen peroxide molecule's shape. In this question, they ask you to draw the shape, so you have to draw the shape. The reason for this specific shape was explained earlier with the use of how electron pairs are arranged around the oxygen atom. Now, in our next question, they ask you to write the balanced chemical equations for the reactions mentioned from A to E. So basically, you have to mention all of these reactions equations, A, B, C, D, and E. So let's quickly move on to the very first reaction that we have. The very first reaction we have is MnO4 minus is turning to be Mn2 plus. So if you remember, MnO4 minus has an oxidation state of +7, Mn2 plus is +2. And the difference between the two is 5 oxidation states. Actually, it is a reduction, so therefore you can expect the manganate or permanganate ion to take up 5 electrons. Right, so that is what is expected over here. Now, let's try and balance this equation. And keep in mind, this is happening in acidic medium. So therefore, when it comes to balancing this equation, you can add H plus whenever you need to balance the number of hydrogens. So you have 4 oxygen atoms here on the left hand side of the equation. So we can add 4 water molecules to balance the number of oxygen atoms over here. And when you do that, the number of hydrogen atoms go up to 8 on the right hand side of the equation, which means we have to have exactly the same number of hydrogen atoms in the left hand side of the equation as well. So to get to that number, we can add H pluses onto the left hand side. Why? Because we have this reaction happening in acidic medium. So now let's check if the reaction is balanced. We have altogether 8 hydrogens on the left hand side, and right hand side we have 8 hydrogens as well. On the right side we have 1 Mn, on the left hand side there's 1 Mn. If you take a look at oxygens, there are 4 oxygens here, and over here as well you have 4 oxygens. After balancing the number of atoms on either side of the arrow, we can take a look at the charges. So we have on the left hand side we have 5 negative charges, 8 positive charges, and 1 negative charge over here as well, right? So basically when you add them all together, you're going to get to an overall charge of +2. Over here you have a +2 overall charge. So therefore the charges on either side is also balanced. Now we can move on to the second half equation, which is hydrogen peroxide turning into oxygen. So the number of oxygens are balanced over here. So you can actually add H pluses to balance the number of hydrogens on the right hand side. When you do that, the charges are not balanced. So to balance the charges, we have to see what the charge of the left hand side is. 0. Right hand side, +2. So to remove this +2, or whenever we are trying to balance charges, we can add electrons. To balance the +2 charge on the right hand side, we can add 2 electrons to the right hand side. Now the equation is balanced. Now students, at this point you can actually add these two together. So when you're adding these two together, you can see the number of electrons on each of these equations are not balanced. So one of the things that you should keep in mind is when you're adding half equations together, the number of electrons in each of the half equations should cancel off the electrons in the other half equation. So since they are not the same, we have to make sure that you multiply each of these equations with the relevant number to cancel off the electrons. So the first reaction should be multiplied by 2 and the second reaction should be multiplied by 5. And when you do that, you can actually get to this following equation. You can get to 2MnO4 minus and 5H2O2 going to 2Mn2 plus and 5O2. And then we have other reactants like water and H plus on either side. So if you take this water, it should be multiplied by 2. So you have 8H2O. This reaction was getting multiplied by 2. So therefore on this side you have 16 H pluses. And this was getting multiplied by 5. So therefore there's 10 H pluses. So 16 minus 10 is going to give us 6 H pluses on the left hand side. Now we can see if this entire equation is balanced. So you have 6 H pluses or 6 hydrogens here and then 10 hydrogens here. So therefore on the left hand side there was 16 hydrogens and right hand side also we have 16 hydrogens. If you take a look at manganese, there are 2 manganese here. Manganese is balanced. Oxygens, we have 8 oxygens here, and in hydrogen peroxide 5 into 2 is going to be 10 oxygens. So 10 plus 8 is 18 oxygens on the left hand side. On the right hand side also you can see there's exactly 18 oxygens. So this equation is fully balanced. This equation is going to be considered fully balanced. So this is the first equation. So if you have written this equation as your equation for A, this is correct. This is the equation or ionic equation for the first reaction. So the equation B, we have MnO4 minus turning into MnO2. So the oxidation number over here is plus 7 of manganese, and this is manganese in plus 4 oxidation state. So for plus 7 to turn into plus 4, there has to be electron uptake of 3, or 3 electrons have to be taken up by permanganate ion. So if you observe the overall charge on the left hand side, it is going to be 4 minus. There's 1 negative charge over here, 3 electrons here, so it's 4 minus. On the right hand side, it is not having any charge. So to balance this charge, you can add 4 hydroxide ions. We can add hydroxide ions in this equation because this equation is happening in alkaline medium. So therefore, now the charges are balanced. However, the number of atoms of oxygens are not balanced. There are 4 oxygens here and 2 oxygens here, altogether 6 oxygens. There's only 4 oxygens over here. So to balance off the oxygens, we can add water. I will first of all bring the 3 electrons here, and we can add 2 water molecules to balance off the oxygens. And now if the hydrogens are balanced, this equation is balanced. So as you can see, 4 hydrogens here, 4 hydrogens there, equation is balanced. So this is the first half equation where the reduction is taking place. And oxidation is going to be happening in H2O2. H2O2 oxidizes to O2. So you can see each oxygen atom goes from -1 to 0. Over here, you can see the oxidation state of oxygen in hydrogen peroxide is -1, and in the oxygen molecule, it is 0. So there are 2 oxygen atoms with -1 oxidation state turning into 0 oxidation state. So there is 2 electrons that are released. So we have 2 electrons released over here. So when you have 2 negative charges on the right hand side of the equation, that has to be balanced on the left hand side as well. So since this is happening in alkaline medium, we can add OH minus ions to the left hand side of the equation. So when you add 2 hydroxide ions to the left hand side, now you can see the number of charges on either side is balanced. We have 2 negative charges here and 2 negative charges on the right hand side as well. However, the number of oxygens is not balanced. There are 4 oxygen atoms on the left hand side and there's only 2 oxygen atoms on the right hand side. So to balance this, we can add water. We can add 2 water molecules. But now students, if you pay attention, we can see even the hydrogen atoms on either side is balanced. So therefore, this half equation is also completely balanced. Now you can add them together to get to the final equation. So if you take a look at the first equation, right? If this is the first equation, we call this the first equation, and this is the second one. The electrons that are involved in each of these equations are not the same. So to bring those electrons to the same value, you have to multiply the first equation by 2 and the second equation by 3. So when you do this, you get to 2 MnO4 minus ions and 3 H2O2 ions, and over here you have 2 MnO2 plus 3 O2, and we can now see there's water over here as well as here. So when you multiply this by 2, it's going to be 4 water molecules. Here it's going to be 6 water molecules. So therefore 6 minus 4 is going to be 2 H2O. And apart from that, if you take OH minus, on the right hand side you have 4 multiplied by 2 is 8 OH minuses, and when you multiply this many OH minuses by 3, it's going to be 6 OH minuses. So 8 minus 6 is going to be 2 OH minuses. So you're going to have 2 OH minuses here as well. So now students, you can observe if this equation is balanced, right? So on either side we can see there are 2 Mn on the right hand side. If you take a look at oxygens, there are 8 oxygens added with 6, so that means 14 oxygens on the left hand side. On the right hand side as well, let's see, there are 4 and 6, that is 10, 10 plus 2, 12, 12 plus 2, 14. So on the right hand side also there are 14 oxygens. So students, oxygen number is balanced. Hydrogen number, there are 6 hydrogens here and 4 hydrogens here, along with another 2 hydrogens coming from hydroxide. So 6 hydrogens is balanced, as well as the charges are also balanced. Left hand side there's 2 negative charges, right hand side also there are 2 negative charges. So this, bear with me, so this is your equation for reaction B. Now let's move on to the equation C. So in the C part, what is taking place is you have bromide ions turning into bromine, right? So we will take 2 bromide ions, and the number of electrons that is released is 2 electrons. So very simple equation, half equation. You can very easily get to it. And then we have hydrogen peroxide. In this case, we can see bromine was getting oxidized, so that means hydrogen peroxide is getting reduced. So it can get reduced to water. Hydrogen peroxide turns into water. So over here, if you observe, oxidation state of oxygen is 1 minus, and when it comes to oxygen in water, it's going to be 2 minus. So from 1 minus to 2 minus, there is definitely going to be a reduction. So as bromine is getting oxidized, hydrogen peroxide is getting reduced in this particular reaction. So on the left hand side of the equation, there are two oxygens. So to match with the two oxygens, we can have two water molecules on the right hand side. To balance of the hydrogens, you can add two H pluses to the left hand side of the equation. And at this point, you would notice the number of electrons are not balanced. To balance the number of electrons, you can add two electrons to the left hand side. And at this point, you are pretty much finished with writing the whole equation. As you can see, reaction number 1 and 2 both have the same number of electron involvement, meaning if you are to add them together, these two electrons will perfectly cancel off one another. So therefore, you are going to get to the following equation, which is 2H plus H2O2 plus 2Br minus is going to become bromine or Br2 plus 2H2O. So this is the equation for your C reaction. If you have written this, this is your answer for the C reaction. And then we have a D reaction. Now in the D part of the reaction, we see hydrogen peroxide. They say decomposes under UV light into water and oxygen. So students, you have to keep in mind hydrogen peroxide has the ability to get oxidized and reduced at the same time. So if you like to write the half equations for that, we can write like this: H2O2. We have already written one of the half equations above where it turns into water, right? Just a little while ago we wrote this. So this is where hydrogen peroxide is getting reduced. And if you take a look at how hydrogen peroxide is getting oxidized, we can write it like this: H2O2 turns into O2, and then we can see the number of oxygens are already balanced. So therefore you have to get two H pluses, and to balance off the charges we have to take two electrons. This equation was also written earlier on in a previous part of the same question. So now what is left for us to do is to add the two equations together. So when you do that, you would notice, when you're adding these two together, you would notice these H pluses on either side, they get cancelled off, and electrons also perfectly gets cancelled off, and the final equation that you're getting is this: 2H2O2 turns into 2H2O plus O2. Now we can see if the number of hydrogens and oxygens are balanced. There are 4 hydrogens on the left hand side. On the right hand side also there are 4 hydrogens. There are 4 oxygens on the left hand side. On the right hand side also there are 4 oxygens. So this is your reaction. But if you observe closely, you would notice the same compound or the same atom undergoes both a reduction to 2 minus and an oxidation to 0. So this is a reduction of oxygen's oxidation number, and this is a oxidation. from -1 to 0 is an oxidation. So students, what do you notice here? The same chemical species, the same atom with a specific oxidation number has undergone both oxidation and reduction. So the next question what they ask is, what type of reaction is this? So whenever you see a situation like this where the same chemical species undergoes both oxidation and reduction, it is referred to as a disproportionation reaction. It is referred to as a disproportionation reaction. Right, so this is a disproportionation reaction. So students, this is your reaction that you see in your D part. We have discussed 4 reactions by now. So the last reaction that they're talking to you about is where you have lead carbonate, right? We start with lead carbonate. They say there was lead carbonate, PbCO3, and in the presence of H2S, they said it turned into PbS, lead sulfide, and so we know what gets formed is hydrogen carbonate or carbonic acid. So this is going to be your very first equation under E. And under E, there's another equation that they're referring to. That is, they say, if you take this black color, PbS, and reacts it with Y, in this case, Y is hydrogen peroxide, they say it turns into a white color substance. So sulfur over here can get oxidized into sulfate. So therefore, you can form PbSO4, lead sulfate. And when something is getting oxidized, what happens to hydrogen peroxide? Hydrogen peroxide will reduce. So to what would it reduce? Hydrogen peroxide would reduce to water. So now you can see, if you're trying to balance this equation, now if you take the oxidation number of oxygen in hydrogen peroxide, it is -1, and it has gone to 0. So there are 2 oxygen atoms turning into oxidation state of 0 over here. So therefore 2 electrons are involved. And if you take sulfur, it is present in the oxidation state of -2. Over here, it is present in the oxidation state of +6. So the overall change over here is +8. So from -2 to +6, there are 8 oxygen numbers that have been changed. So from -2 to +6, the increase in oxidation number is 8. So there is involvement of 8 electrons. There's involvement of 8 electrons. So if you observe closely, to match the number of electrons that are involved, you have to multiply this reducing equation by 4. Then the number of electrons will be a match. So if you multiply this by 4, it becomes 4H2O over here, and it's going to be 4. On the left hand side, it's 4H2O2. On the right hand side, it should be 4H2O. So now, if you observe whether the number of atoms on either side is balanced, you would find there's one lead on the right hand side as well, one sulfur on the right hand side as well. On the left hand side, there are 8 hydrogens. On the right hand side, there are 8 hydrogens. That is also balanced. On the left hand side, there are 8 oxygens. On the right hand side, there are 4 here, and another 4 here coming in from water. So therefore, the number of oxygens are also balanced. So these are the 5 main reactions that we saw in this question, and we have written balanced chemical equations for all of those reactions. Now, let's move on to our next question. They're asking what is the reaction type in reaction D belongs to. So we know reaction D was a decomposition reaction, and we saw when this decomposition was taking place, we saw a disproportionation, right? So the answer would be a disproportionation reaction. So for this, if you have just written disproportionation, reaction, you would have obtained that mark. So the answer for that question is disproportionation reaction. Now in this part of the question, they're asking you to mention one use of an aqueous solution of hydrogen peroxide. So hydrogen peroxide is normally used for disinfection purposes, right? That is one of the major uses of hydrogen peroxide. We do use it in chemical reactions for oxidation and a reduction of other chemical species, but apart from that, hydrogen peroxide is mainly used for things like disinfection, when it comes to bleaching of different types of pulps, and even for wastewater treatment, hydrogen peroxide can be used to remove the organic impurities that is present in wastewater. So if you have written down one of those, even just written as disinfection purposes, that is still going to gain you a mark. In this question, they're asking you, why does hydrogen peroxide have a really high boiling point? They're saying, over here, they say pure Y, is a viscous fluid with a boiling point of 150 degrees, and explain the reason for this boiling point. So you have to mention this. So when it comes to hydrogen peroxide, it has this structure, extremely electronegative element. Oxygen is connected to hydrogen. So as you know, the bonds are going to be polarized, delta negative and delta positive over here. Over here also delta negative and delta positive. So when another hydrogen peroxide molecule is nearby, they can form very strong intermolecular forces known as hydrogen bonding. So as you can see, I will indicate it in a different color. There will be very strong hydrogen bonds formed between the hydrogen peroxide molecules. So due to this formation of very strong intermolecular forces referred to as hydrogen bonds, it's going to be very difficult to boil hydrogen peroxide or pure hydrogen peroxide, because you have to break all of these intermolecular forces in order to obtain a phase change, such as from liquid to gas. So students, this is why it is not going to be easy to boil hydrogen peroxide, or this is why hydrogen peroxide has a really high boiling temperature. So when you're explaining this, you have to mention compared to water. Now water, when it comes to forming hydrogen bonding, it originates from the lone pairs that is present on oxygen. So each oxygen over here has two lone pairs, and at the same time hydrogen can take part in forming one hydrogen bond, so this hydrogen atom. So if you take the entire hydrogen peroxide molecule, there is the ability to form altogether 6 hydrogen bonds with another few hydrogen peroxide molecules. As you can see, there's one hydrogen bond that can be formed with one hydrogen atom. There are 2 hydrogen atoms, and there are 2 oxygens, and each oxygen can form 2 hydrogen bonds. Therefore, altogether, this entire molecule can form 6 hydrogen bonds. If you take a water molecule has 1 oxygen and 2 hydrogen. Each hydrogen can make 1 hydrogen bond, and one oxygen molecule can form 2 hydrogen bonds. So therefore only 4 hydrogen bonds can be formed when it comes to water. But when it comes to hydrogen peroxide, you can form 6. So therefore, it is going to be even more difficult to boil pure hydrogen peroxide than boiling water. Right, students, so this is the explanation for the high boiling point observed at this is the explanation for the high boiling point observed in hydrogen peroxide. Students, this brings us to an end to our experiment number 22. In the experiment number 22, we looked at the theory parts revolving around manganese and its different oxidation states. And in the lab, we conducted experiments to observe these different oxidation states and their colors. And in the last session, we looked at some questions to improve your knowledge about the chemistry revolving around manganese. And I hope you have learned all the theory parts that is related to manganese, and I hope that you will be able to answer any question that is related to the chemistry of manganese. I'll see you again in the next experiment.